Well, welcome to the first class. I first want to introduce myself. I'm Melvin Pomerantz. This is very powerful. I'm sure everybody can hear me, right? I like the line, if you can't hear me, please raise your hand. That's a good line, because if you couldn't hear me, how do you know to raise your hand? So people always say that, I don't know why. But the class is 8B. If you're not enrolled in 8B but just want to enjoy it, you're welcome. Our head GSI is Erin Soar. I don't think she's here right now, but she's very helpful and efficient. So if you have problems, please see her. If that doesn't help you get resolved, see me. I'm available on email pretty quickly. Some of you already contacted me for one thing or another, and I hope you're okay. If there are any other questions, please contact us. Now, first thing I want to talk about is safety warnings. Namely, you know that Berkeley is in an earthquake zone. We also have fires occasionally. So if there is an emergency, these are the doors to go out. That one, if you can do that, or this one, because they lead to the outside. This one, you go out that door and out through there, and you'll be on the outside. What you don't want to do is go out that door. That's less preferable. You can get out that way, but it's complicated. Some of you came in that door, so you know the way out. Oh, by the way, these slides will be available to you right now. We're being recorded, and you will have access to them on YouTube, so you don't have to copy any of this. And even during the lectures, you don't have to copy these slides. Also, I've made them available to you on bSpace, but the fact of the matter is I keep changing things all the time, so that these are modified. And if I get some feedback from you, I may change them again. So occasionally, you'll see that, say, this particular bSpace slide has been modified and changed. So you'll keep getting updated things, which is actually a good message, because that's the way science works. I'm not embarrassed to change things when I see that the need is there. So, and I hope that this is a message you'll get. This is the first message in this class. Be open-minded, flexible, keep changing, keep growing, and that'll make your scientific life that much better. I think all of you are in the sciences or related fields, and I think that's our motto, that's our creed, that we learn from experience and we keep advancing. I make that point a few times in this introduction. So the other thing is that the university provides us with psychological help. It's a pretty stressful time in your life. You're probably taking a lot of heavy-duty courses, bio, organic chemistry, all that sort of thing, and it's a load. I've been through it, I know what it's like. So it was a while ago, mind you, but I remember. And if it's too much, don't freak out. It's only part of your life. It's not the end of your life. It's just a stage. You'll pass through it, just like there were bad times when you were 14 years old. There'll be bad times now, too. But you'll get through it. You remember those bad times when you were 14. You'll get through it. So don't panic. If you need help, come to, well, I'm not the best person, perhaps, but there's a tank center, and there are professionals who will help you, and don't be embarrassed. It's better than some other alternatives. So the university is very conscious of this, and we're all here. Actually, we're here to help you to get through, learn stuff, and move on in your life and go on to a good life. So please keep that in mind. Don't take it seriously, but it's not such a big deal. Okay, and enjoy it. Actually, I'm hoping that this will be an enjoyable course for you, and it should be. Now, some of the bad things, we have to deal with grades. And it's very important to a lot of you. But let me be upfront about how the course is graded. The department requires that we have roughly the distribution of A's, B's, and C's in proportion I show here, about a quarter A's, B's, and then C's, and anybody who does worse than C may fail if you do really badly. But I would not take this, again, too seriously. It's important, it looks good on your grade point average, but frankly, a lot of you are interested in more advanced things. So some of you want to become doctors. You'll have to take the MCAT test. The MCAT test, you're really not competing against the person sitting next to you. You're competing against the kids at Harvard and Princeton and MIT, things like that. So what you want to do, concentrate on, is learning stuff. And then when it comes time to prove yourself, you'll prove yourself against them. And that's really what's important. So if you get a B in this course, doesn't mean that you can't go on to medical school. I've had some very good students got B's, went on to medical school, and did quite well. If you get an A, it means you perhaps learn more. But the point is, you will do very well if you learn a lot and prove yourself on the national scale. Take a big view of it. So that means that you can work with each other to help each other learn, not necessarily get a good grade. Good grades will follow if you learn. That's pretty obvious. Okay, now some of you had a little difficulty with the course ID. I mean, I entered it with some lowercase letters, and Mastering Physics converted them to uppercase, and then it started to work. So I hope most of you got it okay, finally, I think so. And the other thing that you're required to go to discussion groups, you should have had one yesterday for those who are on the Thursday schedule. You should have one today, those are on the Friday schedule, and you have to go next week also. Mostly it's just for us to keep track of who's really serious about staying in the course, because there are other people who want to join, and if we have a name but no student taking it, we'd like to open that space and have somebody come in. Also, if you want to drop the course without penalty, for some reason, that no penalty drop date is next Friday. So you can just drop the course and it doesn't show. But after that, you're not allowed to drop. So that's pretty serious. I hope to stay. Hopefully you'll have fun here. Okay, and then the distribution. This is all. A lot of this information is in the course information online, but the first midterm will count 20%. It will cover, I think, the first 5 chapters that we do. It won't be overly heavily weighted, although it's a little bit late in the semester. So I think it's after like the 8th week. But I won't give you 8 weeks worth of stuff on that first exam, because 8 weeks is about half the course. And so I don't want to heavily weight that first exam. So the first exam will be, I'll explain as we go along. It will be balanced to be about worth 20% of the course. The second exam is also worth about 20%. It'll cover about the same number of chapters. And the final exam is worth 40%. It will cover the last third of the course, about equal to the first 2, and plus sort of cumulative study. On the exams, you'll be allowed, we'll give you more details as time comes, you'll be allowed to have a sheet of notes, 1 sheet for each section of the course. So a total of 3 sheets. On the first side, you'll put down formulas, whatever information you want. Second exam, you write on the back side of it, so you'll have both sets of notes. I find that a very good way to learn, actually, to summarize the course and put down the key things. And if you know the key ideas, that'll be good enough. You don't have to remember every little jot and tittle of the course. If you get the main ideas, which will be summarized on the 1 sheet, and you think clearly, you should be able to do the exam quite nicely, I hope. So that'll be the thing. In the exams, you will not be allowed any electronic devices at all, no calculators or blue books. You'll write the exams right on the exam. So that's, in other words, any math that you have to do, like actual calculating, will be simple enough that you can do it in your head. Or the fact of the matter is, we don't take that much into account. If you've got the problem set up and you end up with a formula or a calculation, say 12 times 6 divided by 18, and you leave it like that, you don't even have to work out the division. I do believe you know how to do multiplication and division. So you can leave it like that to get full credit. Because then you don't need a calculator. set the thing up and have the numbers in there. Good enough. You've done your share. So in order to do well, I would say that you want to talk to people. So I find that a very good way. First of all, you can talk to people who know more than you do. Hopefully the GSIs, myself, others, because we've been through it once before, or friends who've been through it, and they can hopefully give you answers that you can't get. I find a very good way to learn is try to teach it to somebody who doesn't know as much as you do. Because if you try to explain it to them, you see what's coming out of your mouth, and you say, did I say that? Is that reasonable? You sort of learn by teaching. It's a very good way to learn. So if you get some poor victim to listen to you talking about AP, torture them and explain it to them. And no, it's not torture. Look what I just learned, blah, 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 and explain it, and it's good. It's a very good way to learn. But otherwise, you can go to the GSI, any other office hours which are posted. My office hours are also posted, I did before. Or I'll say after class, as long as anybody wants to talk, I spend an hour sitting outside talking to people. It's fine. If you want to talk about stuff, that's great. But okay, now it's good to talk to each other to learn, but when you do your homework, I want the answers to be your answers because your name is attached. And when you do your exams, it's got to be your work. We really do not like people cheating, and we're pretty tough on that. There's a recent UC Code of Conduct which was promulgated in April, and we expect honesty, integrity, and respect for others, meaning, to me, that respect for others means that you, I try to protect the honest people. I don't want anybody who's cheating to get a higher grade and diminish the value of a person who's honest. So I had the unfortunate experience of catching someone cheating last semester, and he flunked, and he had to go home and explain to his parents why he got an F. That's very embarrassing. I got an F because I cheated. Wow. I didn't want to do it, but I'm protecting the good kids. Okay, so the other resources you will have, aside from the textbook and me speaking to you right like this, is that these lectures are being recorded right now. These slides are being recorded right now. You can get them on YouTube or other means. There are other books that are various degrees of difficulty. I happen to like Paul Hewitt, who's a professor over in San Francisco, and he wrote a very nice book, and he actually did little drawings of his own in the book, very cute. Conceptual Physics. Then Richard Feynman, a great physicist. These two guys, the next two guys are Nobel Prize winners, so they know what they're speaking about. Lectures in physics. You can look up topics there. As I say, they're kind of unusual order. You have to sort of search in the index to find anything you want, but he's very down to earth, at the same time, very accurate. And then Edward Purcell was a professor at Harvard, won a Nobel Prize for magnetic resonance, actually. So MRI, magnetic resonance, everything. He was one of the guys that created that. And he's very, very good. And he wrote this nice book, Lectures in Magnetism, which explains things very well if you need background. Then online, there's a huge amount of stuff. I can give you a couple examples here. There's a professor at Harvard who has his lectures videotaped. You can tune in on him, and he's Dutch, so you'll hear a Dutch accent. You can hear my Brooklyn accent if you just go to lectures. And he does pretty much the same things we do, except we do it better. You can do it. We're Berkeley, right? Okay. Now then there's the office hours. Very valuable. Go talk to somebody face to face. Have it come out of your mouth and let somebody straighten you out, because you may have a lot of misconceptions coming in. Okay, let's go a little further pep talk here on, well, you know what science is, but the thing that I want to emphasize is that some of you come in thinking that physics is somehow hard or beyond you. By the way, how many of you actually had a physics course before, like AP or high school? Most of you. Oh, okay, including electricity and magnetism, right? Yes, so, yeah. So most of you have seen some of this before. You may not learn much more, but I would say this. There are a lot of misconceptions sort of in the real world. So you may have had a course, but it may not have sunk in that this is a little different from the real world. We'll get into that a little further. But I just want to tell you, if you don't already know, that physics just talks about our real physical world. We're not going to talk about some imaginary thing that you've never encountered. I think you saw that already in 8D. I mean, you studied about projectile motion. Well, you don't often throw a javelin, maybe some of you do, and projectiles, or have a water hose and you see parabolic flow. But that's the real world. And we don't talk about anything that's completely out of nature. But sometimes we use a little imagination. Like for a long time, people didn't see atoms. So we have to sort of imagine atoms. Now, in fact, we're able to actually see atoms by various means, individual atoms, and verify that they are. We have like standing atomic microscopes. I don't know if you'll hear about it in this course if you haven't already. But so there's sometimes things that you don't come across, like we'll talk about black holes in astrophysics. Now, none of you have seen a black hole. Like nobody's seen a black hole. That's why it's a black hole. It's invisible. But we think it's there. But we're trying to talk about things that we think, and we have very good evidence that they're there. So it shouldn't be strange. In fact, this course, I like to teach it, and it's the only one I really do anymore, because we're really talking about the things in our experience, like electricity. When you turn on an electric switch, what happens? Why? Where did it all come from? That's what I'd like you to know. And this is our real world. Why is this solid? Why is this a gas? What's holding it all together? You should know those things. As I say here, you can go about not knowing this. It's fine. I like to say they built the Notre Dame Cathedral, 1600 or something, when the people thought that the universe was created by earth, air, fire, and water. Those are the elements. And even with that primitive physics, they were able to build the Notre Dame Cathedral. So you can do a lot, not knowing a lot, like we know. But I don't think they could have got to the moon with that physics. I don't think so. So we have extra power. We're going to deliver here all the stuff that sort of happened around 1600. So we've got about 500 years of knowledge. A lot of the world is still living with the knowledge previous to that. And they're okay, they live, they eat, they sleep, everything's good. But on the other hand, there's a limit to how much they can do with that knowledge. With our extra 500 years, which I hope you'll carry out of this class, we can do incredible things, like your cell phone. Isn't it a miracle what an iPhone can do, or this little box here? I mean, and we couldn't do that with the knowledge of earth, air, fire, and water. Not alone by a long shot. So we have tremendous knowledge, and you should love it. You should really love it, because it's a miracle that we know it. But I also want to point out that science is an evolving thing, as I said before, and there's a lot of things we don't know. And there's a lot of things that, for example, we're going to talk about in this class soon, electric charge. We don't know exactly what electric charge is, where it comes from, why it comes in discrete units, like the electron, why there are only two types, plus and minus, we'll talk about. We've seen it before. Why is the universe electrically neutral? Why there are many pluses and minuses? Now, one answer could be that if we're very much different, the universe, as we know it, or life exists, could not occur. That's called the anthropic principle. The fact that we're even here suggests that only a certain kind of universe would allow us to be here. Because let's say the universe, suppose there was more electric charge, negative charge than positive charge. And we know that, and you'll see, negative charges repel each other, right? So if everything was repelling each other, nothing would stick. So you couldn't have a universe that had too much electric negative charge, more than positive. So maybe there was such a universe, but it's all flying apart. But maybe we got lucky and we happen to end up in a universe where those were balanced, and here we are. And a lot of things like that, if a lot of things were a little bit different, we would have a very different universe. We might not be what we are. The anthropic meaning, the fact that there are people here to tell the tale, means that only certain kinds of universes would allow that. So that's but personally, I think some of these things are very basic, like the fact that the electric charge has a certain value, the speed of light has a certain value. I bet there is a real answer, a simple answer for why that is. I don't know it. Nobody knows it. If you get it, you'll win a Nobel Prize. I can't guarantee you, if you can explain any of these things. But as of now, we don't know. So what we'll be talking about are things that we think we know. Some relatively simple things, like the things you had in 8A. They're simple, but they're profound, like Newton's laws, or the laws of thermodynamics. Now, those were the laws that enabled us to do remarkable things, like land this Curiosity rover on Mars. You know the story that happened a couple of years ago. They had this rocket ship which left Earth, shot toward Mars. Mars is a moving planet. It took about 2 years to get there, or something. And they aimed it at a crater. They wanted to land inside a crater on this moving planet. Can you imagine doing something like that? Wow. I mean, and they did it. Things were bouncing down, and it's walking around inside that crater now. That's awesome. And what they use is Newton's laws, F equals ma. You have to get a certain acceleration, give you a certain velocity, and you plot the trajectory in the gravity field of the sun and the Earth and Mars, so that it can come. You know the forces, you know the speed, you steer it around, you course correct a little bit probably, and then you land inside that particular crater. That's awesome. But all you're really using is simple laws, and we have simple models that work remarkably well. And the reason we can do that is because we have a certain way of thinking now, which they didn't have 500 years ago. Namely, we look for causes. Galileo was the guy who gets the credit. Sometimes he was punished for it, for thinking that things have causes. And he looked for the causes of things. And that's different from an approach which says there's a natural order to things. I'll get into that a little later, but I think it's a very profound change of way of thinking, that you look for causes. Okay, now the motivation, again, I try to say, is that even things you think you know, please keep an open mind. Because there's a lot of wrong ideas out in the real world, or people who think they know something but don't. I know in my own experience, when I was a kid, my parents used to speak about electricity, like they plugged something into the wall and say, you get the juice out of the wall, and your parents talk that way? Well, I'm a little bit more advanced. You know, I learned now that there's a voltage difference, which will explain what voltage is. There's a current flow, there are electrons moving. Maybe that's juice, but we want to go a little deeper than that. So if you have ideas like that, please keep your mind open that it may be a little bit nuanced, different from that. So my job really is to try to, well, partly entertain you, partly to explain in other words what the book is saying. The book is good. It's a little bit brief. He titled the book, well, it's Essentials. He really has this essential ideas. And I'm trying to give you some extra feeling for the things that are going on, as well as try to connect more than he does with real-life things, like why the lights go on when you throw a switch. What is on your electric bill? Nice to know. How your electric system in your car works when you turn the key. Why does it do what it does? How did that happen? What's going on there? You should know those. It's nice to know. You don't have to know it, but it's good. I mean, if you get stuck in the dark someplace, you might want to know how your car starts. Now, the other thing, though, I don't want to get too far away from your major interest, which is biology, I gather. So I try to think in terms of how can I relate this to you as a doctor. So let's say somebody's going to be a doctor. Well, let's put it in medical terms. We're going to set you problems where you're going to be given certain facts. Some of them relevant, some of them not. As a doctor, a patient walks in and presents with certain symptoms. So you're going to have to sort out the symptoms, what's relevant and what's not. You analyze or diagnose the problem. You prescribe a treatment, which means you work out the problem. And then you go back, like my doctor sometimes says, take these pills for 2 days. If you don't feel better, come back. So what you want to do is assess the problem. Does it make sense? So that's what a medical doctor would do. That's just normal, I would say, logical problem solving. And that's, if you want to think of it that way. So this course will be very good practice for you, for those of you who want to be doctors. And I hope you follow it because your patients will appreciate it. Now, again, I can't overemphasize the need to understand the meaning of the words. Because when the physicists try to explain the world, they're limited in their vocabulary. They have to use the words that they have. So we use words out of the common language. But in science, we make very specific, accurate, measurable definitions of words. And they may differ from the common language. For example, I subscribe to this word of the day. They send me a word and learn the words. And one word they had was, what is a letter that descended of the word ergon that is a synonym of power? Now, if you see ERG, that's erg. You may remember from 8A, erg is a unit of energy. So you can sort of see where ergon might be related to energy. And then they say there's a synonym of power. And then in this online thing, they define, so that yes, the answer is that from ergon you can get energy, which is a synonym of power, but not in physics. Energy and power are very different things in physics. Power, you'll come across quite a bit here. Power is energy per unit time. So in other words, if I lift a thing and walk up a hill, I have given energy to this object. Now, if it takes me a day to get up the hill, I haven't used much power. But if I run up the hill, I use more power, but I get the same energy. The thing at the top will have the same energy whether I run up the hill or walk up the hill. But it takes me more power to do it. But the energy of